So my role in all of this is I was going to give you guys kind of a brief overview of kind of groundwater hydrology. So when you hear various terms and things like that, you'll feel comfortable in answering questions or kind of understanding exactly what maybe somebody's trying to say or trying to talk about. And Dr. Tagvi and Sali actually got us this little thing. I think he put it together last night. So we're going to use that just a little bit. I had a really great groundwater hydrology professor at Colorado State. And the first day of class, he told everybody, all right, everybody close your eyes. But I'm not going to require you guys to close your eyes because you might go to sleep on me. But he said, what do you see? And everybody was like, well, I don't see anything. And he was like, exactly. And that's groundwater. Okay? So when, one of the troubles that we have is with surface water, it's easy to see. Right? Surface water is there, you discharge it, somebody can see it, you can visually see it, you can figure out what the lake levels are. With groundwater, who knows, right? If I tell you something's happening underneath the ground, it's going to be really hard for you to prove me wrong, okay? And so that was another reason why he said it was a very good field to go into, by the way, because it was hard for people to prove you wrong. So, when we talk about groundwater, we do have to talk about how it relates to the hydrologic cycle. Because we're a little bit limited on time this morning, I'm not going to go into this much, but I want you to think about this. We've all heard about the hydrologic cycle. We teach our kids about the hydrologic cycle now, whether it's in class or in Boy Scouts or Girl Scouts or whatever program 4-H that we do. But groundwater is a big component of that. All right, and so I want you to kind of keep that in mind, that groundwater is a part of that cycle that's going on within our hydrology. And if we look at where the water is, and Larry covered this quite well specifically for the state of Oklahoma. This is on more of a global scale, but groundwater is about 30% globally of our water supplies that we have available. So it makes up a large percentage of the available water. Now, groundwater is typically going to be managed on what's referred to as a basin. You also hear with surface water, you hear about watersheds and those type of things. But groundwater is usually referred to as either a single aquifer or a group of aquifers that's called a basin. And one of the probably most famous ones, I always give my class this one on a quiz, right? This large one right here is the Ogallala, right? And so the Ogallala or the High Plains Aquifer, it would be a groundwater basin, all right? And a lot of times, and we'll talk about this more here in just a second, but groundwater is a lot of times actually the source of the flow that's in rivers most of the time. When we don't have precipitation events, you have water that's in the river, that's actually groundwater that's coming out. And it's just like the lake. Sali did not spit in this lake, okay? He actually put water through this groundwater and it will actually seep up into this lake. So water that's in lakes and water that's in rivers and streams a lot of times is actually water that's actually being discharged from the groundwater system. Okay, we're going to spend actually quite a bit of time on this one. This is actually the definition of an aquifer, okay? And the easiest thing to think about, I went to an in-service training we had for youth water education. We had some guys from San Antonio come up, and the guys from San Antonio were talking about how this aquifer is this big underground hole. Well, that might be right in San Antonio where they have limestone and karst aquifer systems, but what we're really talking about is exactly what this little diagram, this little thing is showing you. It's really just water that's stored within the void space of those soil particles. So when you have soil particles and you put them together, you can't put them together where they're completely meshed together. So there's a little space between them, and the water will actually seep down into that space. And that's, for the most part, in Oklahoma, this is what we're dealing with, okay? So an aquifer is nothing more than, basically, think about it as soil, and it has to contain water, and it also has to transmit water. Those are the two requirements for it to be an aquifer. It's got to hold the water in, but it's also got to let the water out, and water's got to be able to move through it. Otherwise, by definition, it's not an aquifer. Okay, now you're going to hear about lots of different types of aquifers as we go through here. So there's something that's referred to, let's see, where do we want to start? The first one is something referred to as an unconfined aquifer. All right, and when hydrologists make up definitions, they make them as easy as they can possibly make them so that we can remember it, okay? So unconfined means it's not confined on both the top and the bottom, Okay, so there's a layer underneath here, some kind of a clay layer or something like that. And clay can hold water, but clay doesn't transmit the water. It doesn't allow the water to move through it. And so an unconfined aquifer is just an aquifer that basically is not confined on the top. It's only confined on the bottom. All right? And if I poke, I should have brought my monitoring well. I always bring my monitoring well when I teach groundwater. If I poke a hole in this unconfined aquifer, so this is our little monitoring well. This would be a pipe that's in the ground and it's got little slots cut in it so the water can flow into that pipe. If I poke it into this guy, the water level will rise up to a level known as the water table. Okay, so that's an unconfined. Now the other type of aquifer that you'll see, and these can be laid on top of each other. There can be multiple sequences of confined aquifers underneath here. The other type is this confined aquifer, and unlike an unconfined, it's got layers on both the top and the bottom. Okay. Typically what happens in a confined aquifer is you get a recharge area that's way over to the side over here. Okay? So you get water that's coming in over here from the surface and it's flowing in, and by the time we get over here, it's like being in a swimming pool, right? Where you got a cap on the top and the bottom of a swimming pool and you're swimming underneath here. There's a lot of pressure on you. Okay? And so the water that's in this confined aquifer is actually pressurized. Okay, it's under pressure. So if I poke a hole, let's see, we've got one over here. So if I poke a hole in here with a well, and this is slotted, the water will actually move into this well and it will actually rise up to a surface and it'll actually go beyond the water table in some cases. And this is what we refer to as, this is called the piezometric surface. That's one of the only definitions hydrologists didn't make easy. Okay, that's a pretty hard term. So that's called the piezometric surface. You guys ever heard of an artesian well? Artesian wells are wells that just continuously flow over time. Basically what you've done in an artesian well is you've either poked a well or there's a spring that's come up. It's the same thing with a spring, but basically this water that's under pressure flows in here, and then the piezometric surface is actually above the ground surface. So if this is the ground surface, it will just continue to flow. It'll continue to flow until this pressure basically drops enough. Okay? So if you're dealing with a confined aquifer, for example, the Ogallala, and parts of it is confined, the recharge zone for the Ogallala may not be right on top of the Ogallala. It may be way away from the Ogallala. Okay, so I've got family that live in Austin, and in Austin you'll go through areas where they'll talk about critical recharge zones, a sensitive recharge area. Okay, those are the areas where they are seeing that it's actually recharging that confined aquifer. Let's see. I think that's about it. You can get areas where you get these little clay lenses that are underneath here, and water will perch. Okay, and so I think that's good for that slide. All right. So again, what I want to make sure to emphasize here is that there are cases where, like the guys in San Antonio we're talking about, where there are caves that are underneath the ground, right, and there are big holes underneath the ground, and we refer to that typically as a karst system. Okay, that's typically a karst system. So we've got some kind of limestone deposits that have kind of, eroded away and dissolved away, and basically you get these kind of conduits that form, and you'll see springs that'll come out. So you can have these over in the eastern part of the state, kind of in the Ozarks. Okay, you'll get these kind of karst systems. So that is one type of aquifer systems. A lot of the aquifer systems you guys might be dealing with, especially from an ag standpoint, are what we refer to as the aquifers that are the alluvial deposits. Okay, so an alluvial deposit, alluvial means what? Anybody know what alluvial means? Yeah, it means next to a river. The materials were laid down by flowing water is basically what it is. And so when you think about a river wants to meander and migrate. It'll actually move back and forth across the floodplain. So those sediments have been laid down by a river system. And those are, for the most part, going to be unconfined aquifers. Okay? And those are going to be interacting with the river system quite a bit. So we have in Oklahoma quite a few alluvial aquifer systems that are very important water supply sources for us. Okay? Okay, so again, aquifer properties, two things about an aquifer. It has to conduct the water. In other words, how fast can the water move through the porous media? And we talk about that as a groundwater hydrologist, we talk about that as a parameter called the hydraulic conductivity. So if you're ever looking through a groundwater report or something like that, they're going to report hydraulic conductivity numbers all the time, okay? And that's just how easy does the water move through that soil. Which one do you guys think has a higher hydraulic conductivity, a sand or a clay? Sand, okay? Typically the bigger the pore space, the easier it is to move through, okay? So a gravel would be even more than a sand, okay? So that's one of the properties. The other properties is storage. How much water can an aquifer hold? So which one has a higher storage capacity, sand or clay? It's actually clay. Good. Okay. Yeah, clay. Most of my undergrads get this wrong. Okay. Good. Okay. So yeah, it's typically a clay, but a clay doesn't allow the water to move. So a clay is not typically considered to be an aquifer material. And there's a couple of different terms that are used that you'll see in reports, things called the specific yield and the storage coefficient. If you're getting to reading groundwater reports, those are basically just referring to how much storage capacity do we have within the aquifer. Okay, so one of the things that we're really interested in with groundwater is, well, what happens when we start pumping water? Okay, so if I put a well in here, and this well actually pokes into this confined aquifer, we can actually start to take water out of this well, and it will actually cause something called drawdown. Okay, so there will be a drawdown response. And if I've got a well here, and I'm a landowner here, and I'm interested in pumping, okay, I could get interference between those two wells. Okay, and that depends on a lot of different things. We'll talk about that here in just a second. But this pumping causes what's called drawdown, and it's actually a cone if you think about it. Okay, if I'm the groundwater well and the aquifer's all around me, when I start pumping, it starts pulling water from all the way around me, and it actually forms a cone as it draws down. And this is either for a confined, or even if I'm in an unconfined, it will cause a drawdown. And drawdown is just how far is this lowered down. So for example, here's a 3D illustration of what that cone would look like. Okay? And the shape of the cone and how far the cone goes out depends on the aquifer, to be honest. Depends on how fast we're pumping it, depends on a lot of different things. We can even have situations to where we can pump a well and it can create a drawdown and start pushing water in, and it can even pull water from streams, okay, if we're pumping out of an unconfined aquifer. So kind of keep these things in mind as we go through today with the rest of the presentations. So I put a slide up here. Does my well influence my neighbor's well? You may get questions like that. And this is called pumping influence. Okay, this is called pumping influence. And based on what I saw from the OWRB, and Chris, you guys can correct me if I'm wrong, but pumping influence is only considered for those basins where you've got a maximum annual yield that's been determined. Okay, so if you don't have a basin with a maximum annual yield, they don't worry about a pumping influence. Okay, but your clientele, the landowners that you work with, they may be concerned about this. And what I would say is, it depends, and it depends on a lot of different things. It depends on the distance between the wells. The closer the wells, right, the more of an influence you're going to have. It depends on the well characteristics. So if we look over here, there's like an illustration here of a pumping well that's in here. So this is the one we could put a little syringe and pull some water out of this well. I don't know if Solly's going to do that for you later. But there may be somebody else that's got another well that goes down here, and he's pulling out from way down here. Okay, so think about it, the idea that this is also, depth related. There are different depths that this thing's happening. Depends on the aquifer properties. It depends on the pumping rates. Depends on whether we have a stream or a lake. In fact, this pumping well could eventually dry out that lake if it pumped hard enough. Okay. I talked about alluvial aquifers. Those are those aquifers that are right next to those stream systems. So we've got an alluvial aquifer out here with a stream. And one of the big things that we really have to think about, I think, in my opinion, as we move forward with groundwater in the state of Oklahoma, is how these, and even in more detail, I know the Water Board is starting to do this in greater detail, but we need to consider how these things interact with each other. So you can't get a situation where the stream is actually recharging the groundwater. Okay, you can get a situation where the groundwater is actually recharging the stream. You can even disconnect it in some cases. But those are kind of the scenarios that you get with respect to those aquifers and groundwater systems interacting. And so when we pump next to a river, so here's my pumping well. Actually solve the math here actually did have my students do this. They put a well in, and the river is actually right here, and you can look at how this cone starts to develop. And as you pump next to this river, what you do is you actually can induce flow from the stream back into the aquifer to satisfy what's going on with this well. And what you can also do is you can actually capture water that would have eventually recharged that stream. You can capture it back in that well. Okay? So very interesting things happen when you start pumping in alluvial aquifers. I did work at the University of Mississippi for a long time, and the city of Memphis is one of the biggest cities that they got the Mississippi River flowing right by there, but the water supply they use is actually deep groundwater. And one of the things that they talked about was that they really like that deep groundwater because it's been down there for 10,000 years. It's been filtered, all the sediments out of it. It's been interacting with all this soil. It's very nice, very good water. What they're concerned about is that they've been pumping it so hard that they're actually maybe pulling Mississippi River water in. They're not so worried about from a sediment perspective, but it may be some other water quality stuff that they're worried about there. So if you get a little bit more details, we could probably kind of help you answer that question about how likely that is. But I would say, yeah, it really depends on, how far that spacing is and what kind of materials they have in terms of that aquifer. So. This is actually a study that was done by Tyson Oshner. One thing I wanted to mention here as we go through here that I want you to keep in mind is the idea of aquifer recharge. There's been a lot of interest right now in how much water actually gets back down. We've had all this precipitation, right? We had all this water that came in, but what is actually the recharge rate that we get going down into those aquifers? This was a study done by Tyson Oshner on a water center funded project, so I really like to put this one up here, being the water center director. But what these are numbers at each of the different mesonet stations. And these are annual recharge, well, they're not even recharge rates. Okay, these are actually what I think he ended up referring to as drainage rates, but these are in millimeters per year. Okay, so if you take this number, so if you have 30 millimeters, right, you divide that by 10, you get to centimeters. So that's 3 centimeters out here. And then you got about 2.54 inches in it. This is about an inch. Okay, this is an inch per year that he estimated is getting back down into that aquifer. Now, he doesn't have the data to go all the way down through all of this material to figure out how much water is getting way down here. He only was estimating this based on the very top. Okay, so this is probably a high number, but it at least gives us an estimate. Okay, and you can look across the state, and what you see across this state, we don't get a lot of recharge. It takes a long time. Okay, it takes a long time to recharge these aquifers. So as we continue to pull more and more and more and more water out, we are not putting water back in at the rate that we're pulling out in a lot of these cases. Okay. I don't know how much Chris is going to go into this, but this gets to be kind of a fairly complicated deal, right? I mean, we've all been. What I showed you today was kind of hypothetical, kind of simple aquifer systems, one pumping well. What happens when you're trying to model an entire watershed, or not a watershed, but an entire basin, right? Where you've got all these wells pumping, they're pumping at different rates, they're pumping at different depths. You've got aquifers that are interacting with the streams. It gets to be a very complicated process, okay? And so a lot of times, and what people will use, and especially the water board will use, and we as scientists will use, our programs, and the most famous program out there is probably ModFlow. And it's basically a groundwater flow model to model all of these basins. So all the aquifers that we have a maximum annual yield study that's been on is pretty much got a ModFlow model that's been developed for it across the state. Okay, but I thought I would point that out just kind of as an FYI. So I'm going to wrap up there. You guys have any questions beyond what we've talked about so far? I'll be around all day. But I wanted to give you kind of a brief overview, right? So if I quizzed you right now, you could tell me what a confined aquifer was. And if I poke a hole in a confined aquifer, the water level is going to rise to where? Piezometric surface, good, yeah. And if we have an unconfined aquifer, I poke a well in it, it's going to rise to the water table, good. You guys have the foundation that you need for me to set you up for these other guys, okay? So these other guys, you're going to rock it now because of that foundation.